Welcome to this session. This session introduces the chapter forces and friction. So I'll start by seeing how to resolve forces into components in problems involving action of forces on objects. So resolving forces. Now, if force is applied on an object, at an angle, to the direction of motion, we can resolve the components of the force that acts in the direction of motion. So the force is applied on an object at an angle. So the key thing here now, the forces we'll be dealing with in this chapter are forces which act on an object at an angle to the direction of motion. Then we can resolve the components of the forces that acts in the direction of motion. For example, consider in this diagram, we have a table. So let this be a table. And then let's have book this table. And then we have a force at this point A. F newtons acting at an angle theta to this book. So in this situation, a book model is a particle. And then this is a table. So we can resolve the forces acting on this book. So if we draw a right angle triangle at this point here, and then call this point B, call this point A, say call this endpoint with the force C, then using Oshachota, so we have this acronym means sine is opposite of hypotenuse. So opposite of hypotenuse, cosine of the angle is the same as adjacent of hypotenuse. And then tan, opposite of adjacent. So using this, with respect to this side, this is opposite with respect to this angle. So this, the sine of this angle, theta, is the same as this side BC or CB over the hypotenuse, and the hypotenuse, the side of the force is F. So which means CB will have F sine theta. So therefore this one will be F sine theta. And then AB, you use cosine. So cosine of the angle theta adjacent, which is AB, over hypotenuse. Hypotenuse is the magnitude of the force, which is F newtons. So that means that AB will be F cosine of theta. So this will be F cosine of theta. So therefore, with respect to this force acting at an angle on this book on the table, the X component of the force is given by F cosine of theta, and then the Y component or the vertical component of the force is F sine of the angle theta with which the force is acting on the book. Another key point to note when you are resolving forces, that the effect of the force in the direction of motion is the length AB. So from this diagram here, so this is the length AB. So because the force is acting at an angle less, but then it's going to the right. So the effect is felt in this length along AB. And then this is called the component of the force in the direction of motion. The component of the force in the direction of motion. So that's what we have. Now, finding the length AB is called resolving the force in the direction of motion. With respect to this example, resolving the force in the direction of motion. So that's what we call resolving of forces. So finding the length or finding the magnitude of the force in the direction of motion. So for example, find the components of the force in part A, the X direction, part B, the Y direction. So given these force diagrams, so we have this axis. So visually the X, this is the Y. And then we have this angle is 40 degrees. And then the magnitude of this force is 9 newtons. So this part A, and then part B. So this is the y, this is the x, and then you have a force of 100 newtons. This angle is 18 degrees. So those are the two problems for us to solve. Now, we'll be doing each part both for x value and y value. So call this, we should have labeled this one Roman 1 and Roman 2. So Roman 1, Roman 2. So find the components of each of the forces in. So Roman 1, the x direction, Roman 2, the y direction. So solution, in the first case, we'll draw a right angle triangle here. And then this is the vertical or along the y-axis, and then this along the x-axis. And from what we have described in this example here, along the x-axis, we have f cos theta. Along the y-axis, we have f sin theta. So therefore, by definition, along the x-axis here, we have 9 cosine of 40 degrees. Along the y-axis, we have 9 sine 40 degrees, because this is along the vertical axis, and the value of f for the force here is 9. So Roman 1, in the x direction, we have x component is 9 cosine of 40 degrees, and that will give us 6.89 4399988 newtons. So that's what we'll have. And then Roman 2, in the y direction, so we'll have 9 sine of 40 degrees, which will give us 9 sine 40, 5.7, 85088,487 newtons. So, which means that then, hence, the magnitude of force, hence the force acting is given by, so x component is 6.894, and then I, that's the x direction, plus the j direction, we have 5.785 j newtons. So that is the magnitude of the force given in part A. For part B, we draw a right angle triangle here. This will be negative 100 cosine of 18 degrees, negative because it's below the x-axis. And then this one will be negative 100 sine of 18 degrees, negative because it is to the left of the x-axis. So B, x direction, so x component is negative 100 and then sine of 18 degrees. So this is the horizontal force. So you'll be negative 100 sine of 18 degrees. That will give us negative 30. Negative 30.90169944 newtons, which is roughly negative 30.90 newtons. These two four significant figures. And then y component, so this part 1, y direction. The y component is, you see this is along the y, this is the direction of y, and this was the direction of x. So negative 100 cosine of 18 degrees. So I'll have negative 100 cosine of 18, which gives us negative 95.10565163 newtons. So to nearest four significant figures, we say this approximately negative 95.11 newtons. So therefore the force is, remember it's given the form Pi plus Qj. So this will be given by P is negative 30.90 in the I direction minus 95.11 in the J direction, and then newtons. So that will be the force defining, or the vector defining the force in part B. And this is the vector defining the force in part A of this problem. Thank you.